So a diagram on the left probably is old, but the concept is more or less same. You have your quantum processor or qubit at very low temperature, and you have a multiplexer receiving or sending out the signal via Si MOS to external world. Normally, well, ideally, we hope we can integrate, fabricate everything together on single chip. And because they are fabricated on the single chip, so they must be able to work at the same temperature, 20 milli-K. But because the cooling power is limited, to avoid heat up of the whole system, so maybe the better choice is to place this controller at a stage with a higher cooling power. Okay, because MOSFET is probably the most important electronic component in CMOS. So that's why I'm going to quickly go through the working principle of a MOSFET at low temperature. So before going into the detail, this is the ideal electrical switch. You have 3 terminals to control the device, and when your gate voltage is lower than the threshold, you don't have any current. The current is 0. That means you have 0 static power. Beyond the threshold, you immediately receive very high drain current at this terminal. This step-like characteristic guarantee you to use a smaller supply voltage. You just need a small overdrive here to get this switch on and off. That means if you can have this kind of device, that means your energy efficiency is very high. But that's reality. No, sorry, that's ideal. But this is the reality. That's the basic device we are using in our cell phone, MOSFET. And this is the IV curve it shows. Instead of this step-like slope, it shows a sloppy subthreshold leakage before you reach your threshold voltage and you're on state. That means before you turn your device on, you already are consuming electrical power in this region. And because of this slope, you are not able to scale your VDD, supply voltage, very small. Because if you want to have a higher on-off ratio, you always need to pay a certain amount of overdrive in the gate bias. So compared to this ideal concept, the energy efficiency is not very high. So you need to design this device very carefully. So this slope, this leakage current is very important for your application. So this slide explains you why we have this unwanted tail. This is the Venn diagram of a MOSFET along the channel. Here you have source and drain and your channel barrier modulated by your gate bias. And this black dashed line indicates the Fermi level, and you have Fermi tail. That means you can find the electron occupation at higher energy above the Fermi level. So when you gradually apply gate bias, your thermionic electron can gradually passing through overcome this barrier and go to the drain side, contributing the drain current. And this is the reason why you have this tail. And people also say this is the fingerprint of Fermi Dirac distribution present in the IV curve of MOSFET. So, as I said, it's all related to Fermi Dirac distribution. That's the reason why this slope is also a function of temperature, because you change temperature, you change the distribution. When you reduce the temperature, this value, this device parameter is getting smaller. That means the steeper subthreshold slope. That's what we want. And this is the experimental result. When you decrease temperature from 300K down to 4K, you can see the slope is getting steeper. And you also see the current, current is higher. That's because less phonon scattering when you reduce the temperature. So according to this formula, this is ideal, and your slope can be decreased linearly with temperature. But this is, the reality is not perfect. So that's the measurement result. Your swing at first can scale linearly with temperature at higher temperature, but at beyond certain low temperature, the swing saturates. The reason is that on the right-hand side, I show you a band diagram from source to channel, and the black line indicate the conduction band MOSFET, and you have a high density of state in the conduction band, and the no density of state within the band gap. Because of the imperfection of the material, for example, you have dopant, you have phonon, and you have lattice periodicity truncate at the oxide interface. So you induce band tail below the CBM. Because you have this small energy window, like the electron can pass through this small channel, contribute more leakage current on the subthreshold current. So that's the reason why you see this subthreshold swing saturation at low temperature. Another mechanism introduced more subthreshold current is quantum tunneling. When you reduce the tunneling, the source drain direction or the channel region, the tunneling probability increases. And you can also see the tunneling current increase with decreasing the channel length by calculation. And here, if your channel length is 5 nanometer, your drain current is hardly modulated by the gate potential. But if the channel length increase up to 15 nanometer, you see a better on-off ratio. Okay. Then I show you our recent result. We want to study the impact of temperature on the tunneling current, source to drain, direct tunneling current. We use this toy model and solve the boson equation and the current equation self-consistently by changing the temperature from 300K down to 4K, and change the channel length from 25 down to 25 nanometer down to 8 nanometer. This is the result. When your channel length is long, as you can see, the subthreshold current can be decreased by reducing the temperature. And if you extract the subthreshold swing I mentioned before, for this channel length at different temperature, you can see the result here. So you can scale down the subthreshold swing perfectly, almost perfectly with decreasing temperature. But if your channel length is too short, 8 nanometer, for example, your subthreshold current is hard to modulate by your gate, even you decrease your temperature down to 4K. And then you extract the subthreshold swing, and you plot here. You see the subthreshold swing is saturate at very high value. This is not the good news. Okay, left-hand side here, I show you the image of a silicon MOS qubit, and this is the cross-section of the device. To control the qubit, you need multi-fingers, and to operate the quantum dot. But as you know, one of the bottleneck, one of the challenges of the silicon MOS spin qubit is the material quality, because the material quality is degrading the coherent time. So if you want to improve the performance, you need to optimize the material, optimize the process. So to do so, we fabricate 4 different devices, different type of devices with 4 different